Welcome back to another wonderful session. So far today, we have heard from founders, defenders, engineers, builders, hands-on practitioners across the open cloud security community, sharing tools, stories, and hard-won lessons. While this is our second to last talk of the day, it is definitely not one to miss. Ariel Ropek is here and joins us to walk through something critical to getting security right, but often overlooked in practice. I'm guilty of this in person. Testing your detections like they actually matter. Ariel's session is all about bringing end-to-end integration testing into our detection engineering workflows. So you're not just writing rules, you're validating them to make sure your detections hold up in real-world scenarios. The kind of detail that makes your security posture stronger over time. And all sessions will be available on demand starting from tomorrow. But right now, live and in the moment, please welcome Ariel Ropek onto our virtual stage.
Thanks, Matt. Yeah, I'm very excited to be here. Thank you for having me. We're going to be talking about incorporating end-to-end testing into your detection engineering workflow. We are going to look at a few open source tools a little bit later in the presentation, but really I wanted to share some of the methodology and tradecraft that goes into this, because that's also really open source knowledge that can be shared. And that's really the purpose of the talk today. So who am I? I'm Ariel. I have many years in SIEM, threat intelligence, and detection engineering across a variety of product vendors and security service providers over the years. I live in Colorado and I play piano and chess. And if you pay close attention, you might find a little chess-related Easter egg in the presentation here. So let's jump right in. So really what I am noticing in the detection engineering industry really is that detection engineering and software engineering are converging. So a lot of the best practices around software engineering are starting to be picked up in detection engineering. And here are some examples of that. We see a lot of detection as code. So taking a page out of the book of infrastructure as code, where our detections are defined in a code repository, and they benefit from all of the, the things that come along with that, as far as really granular version control, multi-level approvals, and CI/CD integrations with your SIEM or other detection software. So you can be really confident that the changes that you're making to your detection content are well tested, they're approved, they're gated behind multiple levels of approval, and then once they are approved and merged, they get deployed automatically to your detection tools, so you know that everything that is in the software repo is exactly as it is in the tooling. The other thing we're seeing is that detections are more and more frequently code. So back, 5-10 years ago, a lot of the detections were written in proprietary languages, depending on the SIEM vendor that you were attached to. That could have been a specific type of search or query language. Or it could have been, just a user interface that you were forced to click through to create a detection, and there was really no way to export that as a code object. Nowadays, we're seeing much more frequently that detections are written in standard programming languages, whether that's something like SQL, which the previous presenter was touching on, a very common language for interacting with data, or in the case of Panther, using the Python coding language. And a couple of years ago, there was some, I would say, pushback around using Python as a detection language. There was some sentiment that the barrier of entry was a little bit high in terms of, having to learn an actual programming language in order to write a detection. But what we're seeing now, especially with the advent of the LLMs and the generative AI and the code assistants, is that these code assistants are actually very, very good at writing Python and SQL, and they're actually much better at using those common, open languages than they are at using a closed, query language that's specific to a SIEM. Whereas you'd have to do some kind of fine tuning to teach it how to use those languages. But they kind of out of the box, they just know what Python is and can write very, very good Python code. The other thing that we see a lot is unit tests. So this is has been best practice in software engineering for a long time, and it kind of ties in hand with the CI/CD and the code repository practices, where when you make changes to your code base, you have a specific set of unit tests that need to pass before a PR is able to merge, so that you know that your detection logic hasn't been modified or changed, so that's not going to detect the thing that it's supposed to. So you can be really confident that when you merge a PR that has code changes for your detections, it's still going to detect what you want it to detect. And that's a really powerful thing. Before joining Panther, I had not really seen any SIEMs or detection content using unit tests, but I think it's a really powerful thing. And that leads us to the topic of today's talk, is how we can take that to sort of the next level and start doing full end-to-end integration tests, which again is something used in software engineering, where you have your unit tests, they give you a certain level of confidence, but the integration tests give you the full confidence that the code changes you're making when deployed into the ecosystem of software that the system has to interact with are still going to work. And when we apply this to detection engineering, we're not only testing the logic of our detections, we're testing the full threat detection pipeline end to end. So that includes the log collection, all of the log parsing and normalization, as well as the alert delivery pipelines. So unit tests, taking a little bit of a step back, the reason we do unit tests is we want to define the true positive and true negative test cases for detection. So on the right here, we have a little example of what this looks like in PyPanther. Panther is open source Python-based rule language. So we're defining a unit test. This one is for deleting a Amazon Bedrock guardrail. And we can see it's got a name, it has an expected result. So this is the true positive test case. And then this is essentially just a CloudTrail log that, CloudTrail log that when run through the detection will trigger the rule and produce a true positive. And then we'll have another one of these for a false positive. So if a true negative. So that when we run this, we see that it's going to catch the things it's supposed to catch, and it's not going to catch the things that it's not going to catch. So how do we make these? How do we get these unit tests for detections? The traditional way of doing this is very manual. It involves someone like me logging into the system that you want to collect logs from and write your detections against, and performing the action. So in this case, I'd be logging in, I'd be creating a new guardrail, I'd then be deleting the guardrail, I would then log into my SIEM, run a few manual searches, and try to find the logs that were produced by that action. This is oftentimes an iterative process where, the first time it doesn't quite produce the thing you want, you have to go back, try it again. And so we'd like to try to find a way to make that a little bit more efficient. The other way you can do this is using the generative AI tools. There are some downsides and risks to this, in that the AIs have a tendency to hallucinate fields. So with a very common log source like CloudTrail, this is less common. There's a lot of CloudTrail event data in the training data for the LLMs that make it pretty good at recognizing valid fields in terms of, the error code and the error message and things like that. They do have a tendency to hallucinate field values. So I've often seen the models, creating event names for CloudTrail that do not exist, creating, formats or field names that aren't accurate. And that can actually lead to false negatives, which are even worse than false positives. So here's an example of that. This is using Cursor with the latest Claude sonnet. I asked it to produce a unit test for a new rule using the latest AWS VPC endpoint logs, looking for a large outbound data transfer. And it did a pretty good job. It got the event type is correct, the event category is correct. But down here, you can see it created this content length field, which doesn't actually exist in the CloudTrail logs. And so this was a key part of the detection that it wanted to write. And it said, we're going to look for content length greater than a certain number. And it did so very confidently. And it said, this is what the logs will look like. This is what we need to detect on. And when confronted with that, I was like, hey, are you sure about this? And it said, well, yeah, you're right. It's actually not a real field. And rather than, maybe searching for some documentation or doing something to really like make sure it was being accurate, what it did was it modified the rule to look for 3 or 4 different non-existent fields. So it kind of hedged its bets and said, okay, we'll try content length, but we'll also try like data transfer size, and we'll also try bytes transferred, something like that. And actually all 3 of those were non-existent fields. So how can we be a little bit more efficient, but also more confident that the results we're producing are correct? So this is kind of the current process using unit tests, where at the top is kind of the manual process I just described, where we're manually performing an attack, or manually finding the logs, or we're using AI to generate the logs, which again has its own risks. We're then writing the detections, usually using some kind of AI assistant in these days, especially when using these open source languages like Python. We have the CI/CD integration, so the deployment of the detection once it's ready to go is fairly automated. But then once it's deployed, we have to go back in and manually run that attack again. We want to now, like after the detection is deployed, we want to rerun the attack activity to make sure the detection will actually trigger as expected when the malicious activity occurs. And then again, we have to go manually look for those alerts. So what we'd like to do is start with an integration test. So we're going to start by writing an attack integration test. And again, this is something we can do with an AI assistant, and is a lot safer to do this, because if the AI hallucinates something in the integration test, this is an API call that goes out to AWS. And if the API call is malformed or hallucinated in any way, the AWS API will send back an error and say, this is not valid. If you hallucinate a CloudTrail log, there's nothing, on the AWS side that's going to make sure that it's correct. So we're still using these AI tools, but we're passing it through the actual AWS infrastructure to make sure that both the API calls that are being run by integration test work properly, and the CloudTrail logs that are produced are coming directly from CloudTrail. They're not being hallucinated by the AI. So we invest a little bit of extra time at the front end, but that allows us to now, in a very automated way, run the attack, and again, pull those logs from the SIEM using unique identifiers to find what we're looking for. And then we're back to our kind of standard techniques here, where we're writing a detection, we're deploying the detection. But now, since we've spent the effort of writing our integration test, we can simply click the button and rerun it again without having to go manually perform any actions in the console or the system. So let's talk about some open source tools that we've been using to do this. So there's a few that we're using. There are other options for all these things. So again, the methodology is really the important part that I want to share today. But for this kind of mini demo, we're using Panther, which is Panther's fully Pythonic detection language. We're using a tool called Stratus Red Team, which we have forked so that we can create new integration tests. to run against CloudTrail and other cloud providers. And then we're using Grimoire, which is essentially a wrapper for Stratus Red Team, which runs the attack simulations and then automatically pulls back the logs. But again, we're creating a fork of this, and we've modified it to query the Panther data lake rather than CloudTrail directly. And that's one of the current limitations with Grimoire, is that it currently only integrates with CloudTrail. And so even though there are many Stratus Red Team attacks for other providers like Azure and GCP, you can't really use Grimoire with those because it's trying to pull the logs directly from CloudTrail. So we modified it so it's going to pull the logs from Panther. That gives us access to all of the logs in the Panther data lake, including CloudTrail, Azure, all those things. We don't have to rewrite any of the log ingest pipelines because that's all handled by the SIEM. And it also gives the additional benefit that when we pull those logs to use as unit tests, they are going to be post-ingest logs. Whereas if you pull them directly from CloudTrail, they're pre-ingest. And what that means is a lot of times the SIEM will normalize or parse the logs and reformat them slightly. So sometimes if you write a detection based on the raw CloudTrail log, it won't actually be accurate to how the logs look after they're ingested by your SIEM. And this applies to any SIEM, not just Panther. So it's really important when generating these unit tests that you're looking at the post-ingest logs. So let's take a look at an example. We'd like to write a detection for someone deleting an Amazon Bedrock guardrail. So we're going to start with the integration test. And this is a Stratus Red Team attack that I wrote with the help of Cursor. On the left, you see a Terraform file, which is going to spin up the target resource that we're going to attack. And on the right, you see a Go file that's going to perform the malicious API call. So again, the LLMs and the generative AI models are really good at both Terraform and Go. If it hallucinates anything, the AWS API will complain. So we're not gonna be starting from a place of inaccuracy. So once we have that, we use Grimoire to run the attack. And you can see this is our modified version that is using Panther for event lookup. It's going to run that new attack technique that we just created. And then you can see it's going to run this SQL query to pull the logs back from the Panther data lake. It's using a specific unique identifier in the user agent string to make sure that the logs that we pull back are the ones that were generated by the integration test. And then over here on the right, you can see what that looks like. So this now becomes our unit test, which we know is 100% accurate because it came directly from CloudTrail and it was not hallucinated by an AI, and I didn't have to go manually generate this by doing something on my own. So now I bring this into PyPanther, again, using Cursor, and Cursor will very accurately, produce a Python rule that will detect this based on the unit tests that I've provided. The important bit here, where this red arrow is, I've manually added a report that's going to link this detection back to the integration test. And this is what closes the loop, where when we rerun this integration test after the rule has been deployed, we're going to make sure that the detection we expected to fire does fire. And this tag helps the system to know which rules are supposed to fire when the test is run. So now we rerun our Grimoire test, and rather than looking for logs in the data lake, we're looking for alerts. So it's just a slightly modified SQL query, and it's pulling back the alert that was generated. And you can see that tag that was added here. So we know that when we run the Bedrock guardrail delete test, we get the alert that's tagged with that technique, and we close the loop and we say, yes, the detection fired as expected. So this is really powerful for both detection engineering, but it's also something you can reuse later to make sure your detections are working as expected, because the best detection is the one that sits there doing nothing until the bad thing happens. So you really need to run tests like this to make sure that the detection will work as expected when the bad thing happens. So that's it. It was really quick. If you liked the talk and are interested in going deeper, I do have some upcoming talks. There's one in a couple days here online. I'm also speaking at B-Sides Boulder, and we will be doing a more hands-on workshop of this content at some point in the future. So thank you.
Thank you so much.